For centuries, we've looked up at the heavens and seen this perfect, orderly dance of the planets. But the rules of that dance, they were a total mystery, until one brilliant mind finally cracked the cosmic code. So let's dive into the story of Kepler's laws.
It all kicked off with an idea that was simple, really elegant, and, as it turns out, profoundly wrong. You see, going all the way back to the ancient Greeks, the belief was that anything in the heavens had to be perfect. And what's the most perfect shape? A circle, right? Well, that one idea was so powerful it held on for 2 entire millennia. But here's the problem. The planets themselves didn't seem to be playing by the rules. When people actually watched them, their paths looked really complex. Sometimes they even looked like they were moving backward in the sky. So to make this whole perfect circle theory work, astronomers had to invent these incredibly complicated, almost Rube Goldberg-like systems. And this is where it gets really interesting. You had 2 competing models. First, there was Ptolemy's, with the Earth right in the middle. It was a mess of circles spinning on other circles called epicycles. Then Copernicus comes along and, in a revolutionary move, puts the sun at the center. A huge step forward. But even he couldn't shake the idea of perfect circles, which meant his model still wasn't quite right. So, to finally break this 2,000-year-old deadlock, it would take 2 very different kinds of geniuses. You needed one person who could meticulously measure the heavens, and another who could dream up the hidden math behind it all. So on one side, you've got Tycho Brahe. Think of him as the ultimate data guy. He spent his entire life building the world's best observatory and recording the most precise measurements of the planets ever made. And on the other side, there's Johannes Kepler, this brilliant mathematician who was convinced the universe had a secret mathematical song. Tycho had the data, Kepler was hired to find the music in it. Now this is a pivotal moment in the history of science. Kepler worked for years trying to make Tycho's incredibly accurate data on Mars fit a circular orbit. He got so close. His model was off by just 8 minutes of arc. That's a tiny, tiny fraction of a degree. Most people would have just fudged the numbers, but Kepler knew Tycho's data was even more accurate than that. So he did the unthinkable. He threw out his own beautiful theory because it didn't fit the facts. He trusted the data. And that one courageous decision changed everything. It led him to toss out 2,000 years of tradition and discover 3 stunningly simple laws that described how the planets actually move. And what was the answer he found? Boom. Planets don't move in perfect circles. They move in ellipses. This was Kepler's first law, and it was an absolute bombshell that just shattered that ancient idea of perfect heavenly circles. So, what on earth is an ellipse? Honestly, it's simple. Just picture a circle and kind of squish it down a bit. Instead of one center point, it has 2 special points inside called foci. And here's the brilliant part. The sun isn't at the center of the orbit. It's at one of those foci. And that means a planet's distance to the sun is always constantly changing as it goes around. Okay, so that's the shape of the orbit. What about the speed? Well, that brings us to Kepler's second law. Now, the official definition sounds a little technical, but the consequence is super simple and makes perfect sense. Here's what it all boils down to. To cover the same area of space when it's near the sun, a planet has to really book it. It has to move much faster in its orbit. And then, when it's far away, it can take its time and slow right down. So our own planet Earth is actually moving fastest in January and slowest in July. How cool is that? Now, this third law, this is the one that really felt like magic to Kepler. This is where he found that beautiful cosmic harmony he'd been searching for his whole life. It's this incredible mathematical link between how long it takes a planet to go around the sun, its period, and the size of its orbit. And just look at the numbers. It is wild. It doesn't matter if you're talking about Earth or Mars or way out there at Jupiter or Saturn. If you take the time of its orbit and square it, then divide that by its average distance from the sun cubed, you get the exact same number. It's this amazing hidden constant that connects the entire solar system. So, Kepler's laws were a total masterpiece. They explained how the planets moved with incredible accuracy. But they left a giant question mark hanging in the air. Why? Why ellipses? Why do they speed up and slow down? For that answer, we had to wait for the next giant of science to step up. You can really think of this as a perfect handoff in the great relay race of science. Kepler did all the hard work to describe the how. And then, about 70 years later, Isaac Newton came along and delivered the why. And that why, of course, was gravity. Newton proved that the very same force that makes an apple fall to the ground is the invisible string holding the moon in orbit around the Earth, and all the planets in their elliptical paths around the sun. His law of universal gravitation was the physical engine that made every single one of Kepler's laws make perfect sense. Okay, so this is all fantastic history, right? But you might be wondering, why should I care about some 400-year-old laws? Well, the truth is, these laws aren't just history. They are the essential toolkit we use for all modern space travel. I mean it. Literally every single time we send a probe to another planet or launch a GPS satellite or figure out where an asteroid is going, we are using Kepler's 3 laws. They are the fundamental language of orbital mechanics, written 4 centuries ago but spoken by mission controllers every single day. All right, let's do a super quick summary. The key takeaways. 1. Orbits are ellipses, not perfect circles. 2. Planets change speed, moving faster when they get closer to the sun. 3. There's a magic mathematical ratio connecting a planet's year to its distance from the sun. And finally, 4. Newton's gravity is the why behind it all. Kepler's true legacy was his courage to trust the evidence over his own cherished beliefs. And because of that, he uncovered this stunning, hidden symphony in the heavens. It really makes you wonder, as we peer deeper into the universe with tools that Kepler could only dream of, what new cosmic harmonies are out there just waiting to be discovered?